Hello everyone, my name is Rafael, I am an electrical engineer, and in this video I would like to invite you to observe the solution of 6 exercises related to differential equations that frequently appear in exams for electrical engineers. Let's go to the first. Describe the following circuit in the time domain if the switch closes at t equal to 0. Evaluate the case in which the power supply is of a constant value. Okay, my friends, this is the exercise. Let's go to the solution. Applying the voltage law, we get that E of t is equal to 1 over c times the integral of I of t dt plus Ri of t plus L times the derivative with respect to time of I of t. Okay? We are going to differentiate to get rid of this integral for better manipulation, and we get that the derivative with respect to time of E of t is equal to 1 over c times I of t plus r times the derivative with respect to time of I of t plus L times the second derivative of I of t with respect to time. Okay, and since the forcing term, the voltage source is of a constant value, its derivative with respect to time is 0, okay? And then we are going to use this technique, and it becomes a homogeneous differential equation when the forcing term is equal to 0. And else we are going to divide everything by L to make 1 appear here. And the differential equation thus becomes the second derivative with respect to time of I of t plus R over L times the derivative with respect to time of I of t plus 1 over LC times I of t. We're going to use the following technique that is frequently used in control engineering, which is to call alpha equal to R over 2 times L and W0 squared equal to 1 over LC. And in this way, the differential equation becomes the second derivative with respect to time of I of t plus 2 times alpha times the derivative with respect to time of I of t plus W0 squared times I of t equal to 0. This is a homogeneous differential equation when the forcing term is equal to 0. It has no particular solution. It has only the homogeneous solution. And to obtain the homogeneous solution, we do the following. R squared plus 2 times alpha times R plus W0 squared is equal to 0. Okay? And the roots of this equation is going to be, you simply do this, you apply Bhaskara here to calculate the roots of this quadratic equation, and then we find that R1 is equal to negative alpha plus the square root of alpha squared minus W0 squared, and the second root is equal to negative alpha minus alpha squared minus W0 squared. Okay, it's going to be the square root of it all. Alright, these are the roots of the characteristic equation. But the roots can be either real and distinct, they can be equal, and they can be complex conjugates. Let's evaluate both of them. Let's evaluate the three cases. Let's evaluate the three cases. Let's go. There will be three kinds of solutions when the rules are like this. Let's see the first. When alpha squared is greater than w squared. When greater than w squared. Remember that we are evaluating this. R equal to negative alpha plus minus alpha squared minus w0 squared, the square root of this term. Okay, we are evaluating this. When alpha is greater than w0, this term here is real. And the roots are real and distinct. And the homogeneous solution is of the sort k times k1 times e r1t plus k2 times e raised to the power of r2t. Okay, this is the first case, the first homogeneous solution. It is the case for which alpha squared is greater than w squared. Now let's go to the second possibility. The second possibility is when alpha is equal to w0. When alpha is equal to w0, then we have a 0 here, and the roots r1 will be equal to r2, which will be equal to negative alpha. And the roots are equal to negative alpha, and the homogeneous solution is h of t equal to k1 plus k2t e to negative alpha t. All right, and finally the third possibility is when alpha squared is less than w0 squared, and in this case here alpha squared is less than w0 squared, and in this case we have a negative number here. When we have the root of a negative number, we have an imaginary number here. A real number plus minus an imaginary number makes up a complex number. So the roots are complex conjugates, all right? And if we make that WD is equal to J times W0 squared minus alpha squared, the roots will be, R will be minus alpha plus minus JWD. Okay? Here, this J does not exist here. WD is this. WD is this. And JWD is this part, the imaginary part, and alpha is the real part. Okay, we have one root here, which is negative alpha plus JWD, and the second root minus alpha minus JWD. And the solution, the homogeneous solution, is therefore IH of t equal to k times e minus alpha t times the cosine WDT plus an angle. Okay? So we have three possibilities of solution for this homogeneous equation. And it is only possible when the forcing term is constant. If the forcing term is a function of time, then there will be the particular solution, which will depend on the nature of the forcing term. Okay, this was exercise 1. Let's go to exercise 2. Now let's go to exercise 2. Solve the differential equation And the exercise wants us to calculate for these two forcing terms, the cosine and this constant value here. In exercise 1, the forcing term was involved in a derivative, and the derivative of a constant value is 0. Then we did not have for exercise 1 the particular solution, but here we are not taking the derivative of the forcing term. Then we are going to have now a particular solution for this kind of forcing term. Okay, let's find firstly the homogeneous solution, which will serve for both cases. CR plus 1 over R is equal to 0. Okay, and it leads to R equal to minus 1 over RC. And the homogeneous solution is of the sort E0h of t equal to k times e raised to the power of negative t over rc. Okay, this is the homogeneous solution. Now, let's calculate the particular solution for both cases. Letter A first. Okay, as letter A is a constant, we are going to have a particular solution of the sort E0p of t is equal to a constant. A is a constant. What we need to do is to simply substitute this in the original equation, and we get that c times the derivative with respect to time of A plus 1 over R times A equal to 1 amp. Okay? And in this case, the derivative of a constant value is 0. In this case, we find that the constant A is equal to R. Is equal to R. And the general solution for this forcing term here is then E0 of t equal to k over RC plus R. Okay, this is the solution for letter A. Now let's go to letter B. Letter B involves a cosine, and the particular solution must have general terms that involve cosines and sines. Why sine if there is only cosine there? Because we are taking the derivative here, and the derivative of sine is cosine. Okay? The derivative of sine is cosine. If we put the terms here, we must equal them to a cosine here. So we need to use both sine and cosine. Then the particular solution is going to be A times the cosine Wt plus B times the sine Wt. Alright? And in this way, we are making it the most general possible and allowing the solution to cover all possible formats. And then we simply apply this in the original equation as we did before. And then it is the derivative with respect to time of A times the cosine Wt plus B times the sine Wt plus 1 over R times A times the cosine Wt plus B times the sine Wt equal to cosine Wt. Alright? And if we develop this, we get that A is equal to R over 1 plus WRC squared, and B equal to WR squared C divided by 1 plus WRC squared. Using this and this here, we get that the general solution in this case is 0 of t equal to k times e raised to the power of negative t over rc plus r over 1 plus w rc squared times the cosine wt plus wrc sine wt. Okay, this is the general solution for the case in which I of t is cosine t, and this is the general solution in the case the forcing term is of a constant value such as that. Alright, my friends, let's go now to the third exercise. Exercise 3. Find the general solution for the differential equation if the forcing terms are letter A, e raised to the power of 2t, and letter B, 3t squared plus 4t minus 5. Firstly, we are going to find the homogeneous equation, which will serve both cases, and they will be only different in the particular solution. Okay, the homogeneous equation is y double prime minus 2 times y prime minus 3 y equal to 0. Okay, and the characteristic equation is r squared minus 2 times r minus 3 equal to 0. And applying Bhaskara here to find the root of this quadratic equation, we find that r1 is equal to negative 1 and r2 is equal to 3. Okay, these are the roots of this equation here. And with the roots, we can compose the homogeneous equation. And the homogeneous equation is yh of t equal to k1 e raised to the power of minus t plus k2 e raised to 3t. Okay, now let's go to the particular solutions. For letter A, we have to use a term that represents this, okay, that represents this and the configuration here. Alright, since we have a term here of E, we are going to use that the particular solution is equal to a constant times a raised to the power of 2t. And if we apply this in the original equation, we get that the second derivative with respect to time of ae 2t minus 2 times the derivative with respect to time of a 2t minus 3 times a 2t equal to, in this case, e raised to the power of 2t. This is letter A. If we develop this, we find that A is equal to negative 1/3. We have to develop this. I already did. I invite you to try. And in this way, we find that the complete solution for letter A is yh of t equal to k1e minus t plus k2 3t minus 1/3 of e to t. Okay, this is the general solution In the case f of t, the forcing term is equal to e2 to t. Now let's do the same for letter B, okay? It is not going to be hard, it is going to be as easy as letter A. And we have to use a term that represents the forcing term, okay? And we are going to use the following particular solution. Is going to be of the sort for letter B, yp of t is equal to a t squared plus b t plus c, okay? What we need to do to find these constants a, b, and c is to apply this here, okay? So it is going to be the second derivative with respect to time of at squared plus bt plus c minus 2 times the derivative with respect to time of at squared plus bt plus c minus 3 times the at squared plus bt plus c, and this has to be equal to this forcing term here, 3t squared plus 4t minus 5. And we need to develop this. I'm going to invite you to try yourself. I already did, and we find that a is equal to -1, b is equal to 0, and c is equal to 1, and thus the general solution comprising the homogeneous solution and the particular solution will be firstly the particular solution in this case is going to be equal to minus t squared plus 1, okay? We simply put -1 here, 0 here, and 1 here, and we get this. And finally, the general solution is k1 e raised to -t plus k2 3t minus t squared plus 1. Okay, this is the general solution for letter B. This is all for exercise 3. Let's go now to exercise 4. Now let's go to exercise 4. Find the general solution of this differential equation. As always, we begin by finding the homogeneous solution. And to find the homogeneous solution, we set the forcing term as 0. So the derivative with respect to time of y plus 3, y has to be equal to 0, and r plus 3 equal to 0, the characteristic equation, where r is equal to -3. And in this way, the homogeneous solution is equal to k times e raised to the power of -3 times t. Okay? This is the general solution. Now let's work on the particular solution. We have to find a particular solution whose derivative has a term such as this. Okay? So if this is one of the derivatives of the particular solution, then we are going to use the following term. The following particular solution, yp of t, will be a times x squared times e raised to the power of -3x. Okay, I put t here, but in reality it is x. It is x. Okay, and if we put this here, the derivative of this has one term that is similar to this, and then this satisfies our problem. This is a possible solution, and we simply apply this to the original differential equation in this way. And this has to be equal to the forcing term. Alright? And if you develop this, already did, try yourself. I invite you to try yourself. We find that A is equal to 1. Alright, then the particular solution is equal to x squared raised to negative 3x. This is the particular solution, and if we use the particular solution and the homogeneous solution, we find the general solution. The general solution is therefore equal to k minus 3x plus x squared minus 3x, or simply, if you prefer, 3x k plus x squared. Okay, this is the solution of exercise 4. Let's go to exercise 5 now. Let's go to the fifth exercise. The second derivative of y with respect to time plus 4 times the derivative of y with respect to time plus 4 times y is equal to e raised to the power of negative 2t. Firstly, we need to find the homogeneous solution, and the homogeneous solution is found by using the characteristic equation. The characteristic equation is r squared plus 4 times r plus 4 equal to 0. And by applying basically here to calculate the roots of the quadratic equation, we find that r1 is equal to r2, which is equal to 2. When the roots are equal, we apply the following technique. The homogeneous equation is going to be k1 plus k2t e negative 2t. Okay? We're going to have, for one root, we have k1 times e raised to minus 2t. But we have the second root. However, the second root is equal to the first. Then, to not have two equal terms here, we have to multiply 1 by t. Okay? This is the catch here, how to understand this, okay? And if we understand why we need to put the t here, we are going to understand easily the particular solution, okay? I'm going to repeat to you. Ke raised to negative 2t. This is one term. We need to put another term because we have two roots. The quadratic equation has two roots. But the roots are equal. And if I put here another ke raised to negative 2t, they become equal. And this does not reflect the real solution. Then I need to multiply here by a t, okay? This is key to understanding this particular solution, the particular solution of this equation here when we have a forcing term such as this. Alright, so the particular solution, yp of t, is going to be similar to the homogeneous solution. Okay, but we already have two roots here that are equal, and I needed to multiply 1 by t to make it be distinguishable from the first. And this is what we are going to do to distinguish the particular solution from the terms of the homogeneous solution. we are going to use a constant times t squared, okay? We always do this. We always raise the power of t. Here t is 0, here the power of t is 0, here the power of t is 1, and here the power of t is 2, okay? This is the technique that mathematicians use to find the solution of differential equations. And we are going to apply this, okay, the second derivative with respect to time of at squared e plus 4 times the derivative with respect to time of at squared plus 4 times at squared e t equal to e raised to the power of a negative 2t. By developing this, we find that a is equal to a half. And we are going to use this here to find the particular solution, okay? And with the particular solution and the homogeneous solution, we find the general solution or the complete solution. The complete solution will therefore be k1 plus k2t, k1 plus k2t plus a half t squared, it all multiplying the common term, which is the forcing term, t, okay? This is the complete solution of this differential equation. Now let's go to the last, exercise 6. Exercise 6 wants us to find the general solution of the following differential equation. As always, we are going to find firstly the homogeneous solution. The homogeneous solution is easy, and it is simply r plus 3 equal to 0, where r is equal to negative 3, and is 0 h of t equal to k raised to the power of minus 3t. Okay, easy. This is the homogeneous solution, and now we are going to find the particular solution. The particular solution is a little bit harder to find. We are going to understand how we can find this. E0p of t is going to be, okay, first we need to understand that the particular solution must reflect the forcing term, okay, must reflect the forcing term, and its derivatives, because we are going to have to differentiate here and add to this. So we need to have the derivative of sine is cosine. Okay, we can add the derivative of sine with cosine, but if we put sine here, the derivative is cosine. And we are going to add sine with cosine, and it is not cosine. So we need to have the both terms, sine and cosine, because one is the derivative of the other. And with this, we can add them here and here to compose this, okay? You are going to see. We are going to see it is going to be a e minus 3 times the cosine t plus b negative t sine t, okay? If I have both cosine and sine, if I differentiate, I'm going to have again cosine and sine. So I can add the derivative with the function itself. I can add the derivative with the function itself because I have both terms of sine and cosine in the function itself and its derivative. And by adding them, we have the forcing term. So this is the reason why we need to find a particular solution that reflects both the forcing term and the equation. All right? I think you already understood. Let's apply the technique. We need to apply the particular solution in the original equation, and we find that the derivative with respect to time of a raised to minus t cosine t plus b sine t plus 3 times a t cosine t plus b e sine t equal to e cosine t. Okay? We need to develop this. I already did, and I found that a is equal to 2/5 and b is equal to 1/5. And using this here, we discovered the particular solution. Okay, and the general solution is going to be consequently E0 of t equal to k negative 3t. This part here is this, the homogeneous solution, and the next part is the particular solution. And the particular solution reflects the forcing term applied to the system that this differential equation represents. T 2 times the cosine t plus sine t. Okay? Alright, my friends, this is the video that I wanted to make to talk to you about differential equations. I hope you liked it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!